So the very last section we're going to go through is 4.8. And what we want to do is work again with these profit functions, cost functions, stuff like that. But we're going to be able to kind of do more in-depth ones. So if we know a price for a certain thing and we sell a certain number of units, we can come up with a nicer equation to talk about our total cost. So that's going to be our ultimate goal in this lesson. So if we think of a business, after studying 2 years worth of sales records, the owner of a boutique found out that she can sell 400 jars per month of a particular brand of bath beads when she prices them at $12. When she lowered the price to $10, she was able to sell 480 instead. So if we assume the relationship between the price and sales is linear, we can find the price based on the number of bath beads we sell. So in this particular case, we're going to input jars sold and then we're going to output the price. So when you sell 400 jars, you can price them at $12 each. And when the price is $10, we can sell 480 jars. So if we want the equation of this line, we've got to find two things. We've got to find the slope and then ultimately that y-intercept, because the price will equal the slope times the number of jars, which is x, plus that value of the y-intercept. So first, let's begin with finding the slope. We look at the difference in prices. Doesn't matter which one you pick to be first. I'll start with the 10, subtract the 12. Then the x value that corresponds to 10 is 480, subtract the 400. So 10 minus 12 is negative 2. 480 minus 400 is 80. That slope is going to equal negative 0.025. So pretty much as the number of bath beads increases, the price is going to decrease because you're going to sell more jars for a lower price. Right now our equation is the price is equal to negative 0.025 times the number of jars plus b. So we can use either of these 2 points to find that value of b. So I'm going to stick with this first point. The price is going to be 12 when we input 400. So we can solve this equation for b. So when you multiply those out, this is 12 equals negative 10 plus b. Add that over to the other side, and that's going to tell us that 22 equals b. So our price, based on the number of bath jars we sell, is going to be negative 0.025x plus b, which is 22. So now I want to figure out how to come up with an equation for my revenue and then ultimately my profit. So this is just the price per jar based on the number of jars we sell x. The word revenue is going to be that amount of money we take in. So basically, if I sell X units at P price, my revenue is going to be X times the price. So the number of units times the price. Well, what we just did was we found a price based on the units. So our revenue is going to be the number of units X times the price. But we just found an equation for the price. It's negative 0.025x plus 22. So we can go ahead and use our distributive property, distribute that x out, and that gives us negative 0.025. X times x is x squared, and then the x times 22 is 22x. So this is the equation for our revenue. Now the costs come in two different quantities like we've seen before. You have fixed costs like rent, utilities, wages of employees, insurance. Those stay the same regardless of what you make or not. Then you've got variable, which comes from how much you're selling and at what price you're selling them. So based on this, our particular boutique has a fixed monthly cost at $325. So that's the money they have to pay associated to these bath beads. They're going to sell the jar, or the cost from the jar from each supplier is $3.50. So they're going to charge you more than $3.50 so they can make a profit. But at their wholesale, I'm going to have to spend $3.50 for every single bath bar I sell. So this $3.25 is our fixed amount, which is that value of B. And then the $3.50 is based on how many jars you actually sell. So our cost is 3.50 times the number of jars plus 325. So this first piece is our variable cost. It's the cost per jar. And this is our fixed cost. So this does not change. Even if you sell no jars, your cost is 325. So now I have equations for my revenue and for my profit, or for my cost. Your profit is just going to be the difference between the two. So the profit is the total revenue you bring in minus the cost. Well, for us, our revenue is negative 0.025x squared plus 22x. And the cost we just found to be 350x plus 325. But that minus has to go to the total cost. So be careful about your minus signs. You have to put parentheses around the cost function. So if you notice, we do have some pieces that are similar. I have some x's here, I have some x's here. We can really go ahead and simplify this expression by grouping those like pieces. So if we distribute that minus sign out, you get minus 3.50x minus 325. So grouping our like terms, we have 22 x's and then we're getting rid of 3.5 of them. In total, we're going to have 18.5 x's. And then everything else was already the only component like it. So now I have this great formula for the profit function. If I sell 200 jars, I can see what my profit is going to be. So the profit, rewrite it up here, is negative 0.025x squared plus 18.5x minus 325. So if you want the profit from 200 jars, you'd go ahead and plug in 200 for x. Minus 325. And what you find out your profit from selling 200 jars would be 2,375. Now if I bump up my my number of jars and I sell 600, let's see what our profit's going to be. So it's negative 0.25 times 600 squared plus 18.5 times 600 minus 325. So in this case, when you go through and plug this into your calculator, your profit's going to be 1,775. So when I sold 200 jars, my profit was in the 2000s. And when I sold more jars, it was actually worse off for me. And so there's a particular reason why this happens. So to sell jars, you had to lower the price. And because you're lowering the price, you're not making as much profit per jar. So because of that, overall, I'm not getting that same amount. It's going to be better for me to sell the 200 to make more money. So to sell more jars, they had to lower the price per jar. So remember, we had to lower the price from $12 to $10 just to get that $80 increase. So if I'm selling 200 versus 600, I'm going to get a lot less per jar from the 600. So this is good, but how do you figure out what's going to be our max profit then? Or how can I figure out how many jars I should possibly sell? And if I sell no jars, what is that going to tell me too? So if I sell no jars, by plugging this into our profit, using that same function, you plug in 0 for X. And really, you just get negative 325. So this was your fixed cost. If you don't sell any jars, there's no way you can make revenue, and you're not losing money off of the cost per jar. So if they sell no bath beads, we lose $325 in those fixed costs. Okay. And now we're going to try to see how we can figure out this maximum profit. So if you go ahead and plot this function in a calculator, if you do it on the computer, my profit's going to increase, and then it's going to eventually decrease after that. So if I want the maximum profit, I need to figure out what is this number of jars I can possibly sell to make the biggest profit. And so if you look on your computer and you kind of trace it, when X is equal to 370, that's going to be your maximum profit, which is your Y value. So you need to sell about 370 jars. And the largest profit would be 3,097.5. So if we want to see what price we should put at our jars, remember that price, which was little p, was equal to negative 0.025x plus 22. The price for 270 jars, 370 jars, would be $12.75 per jar. So if we want to maximize our profit, we better charge $12.75 per jar. Okay? Now what if we do something different? Maybe we decide we're going to donate the proceeds from 5 sales of the bath beads to a local shelter each month. So in that case, our revenue is no longer the number of jars multiplied by the price. I've really lost 5 jars, so I have X minus 5 that I'm making money off of. The price is still the same per jar, I just have less units. So because of this, we need to be able to multiply it, but how can we do that with these two different things going on? So the expression that results is the product of what we call two binomials. So bi means two, and nomials just talks about them being polynomials. So to understand how we perform this multiplication, let's go ahead and assume the 10 is a number, or the x minus 5 is just a number. Let's make it 10. So I would have 10 times this quantity. The distributive property tells you you'll take 10 times the first piece, 10 times the second piece, and you get exactly this. So we can treat the x minus 5 just like the 10. The 10 got distributed to both pieces. We're going to distribute the x minus 5 to both pieces. So this term gets distributed to the negative 0.025x, and then it gets distributed to the 22. So now what happens is I have to take x minus 5 and multiply it by the negative 0.025x, and same thing, x minus 5 times 22. So now we're going to have to apply the distributive property once again to get a simplified expression. So we have x minus 5 times negative 0.025x, and we're adding to that x minus 5 times 22. So we want to distribute this negative 0.25x to the x and to the 5 as well. So that's going to give us x times negative 0.025. So you get an x times x, which gives you an x squared. And then you have minus 5 times negative 0.025x. Then we do the same thing with this 22, distribute it to the x and the negative 5. So we get plus 22x minus 5 times 22. So now some simplification. It's 0.025x squared. If you do negative 5 times negative 0.025, that will become a positive 0.125x plus 22x, and then 5 times 22 is 110, and it's a minus sign. So we only have two pieces that are alike. These are the x's, the x squareds are on their own, the constants on their own. So if we combine these like terms, we get negative 0.025x squared plus 22.125x minus 110. So this is our simplified expression now to figure out our revenue from losing 5 jars. So this process of multiplying two terms is you distribute the one piece to both of the others, and then you apply the distributive property again. So pretty much each term in the parentheses will come in contact with the other terms from the other parenthesis. So let's go ahead and work with a particular example again. So in designing the boutique's parking lot with a 4-foot landscaping strip on 3 sides, an architect found that the total area could be expressed by this, where W is the width of the paved portion. We want to multiply out the parentheses and simplify the expression. So another method you can use, because each one of these is going to come in contact. So the W is going to come in contact with both of these. The 4 is going to come in contact with both of these. A way you can multiply these expressions is using a process that's called foiling. So F stands for the first terms get multiplied. O is next in FOIL. That's our outer terms. Then it's I, which is our inner terms. And then L, which stands for the last. So I'm going to multiply the first terms together. And this is going to equal W times W, which is W squared. Then if I go for the outer, the W is on the outside, the 8 is on the outside, so you get plus 8W. The I is our inner term, which is a 4 and a 2W. So when you multiply them, 4 times 2W is 8W. And then L is the last, the 4 is the last, and the 8 is the last. Their product is 32. Then you group your like pieces. We have 8W and another 8W. So this simplified expression is W squared plus 16W plus 32. Okay. So the way this form was started is called the factor form of the expression because you have one factor times another. So those make your product. This actual answer we got is the expanded form of the factored form. Okay. Both of these are really just equivalent to each other. They represent the same thing. If you picked values of W, you'd see both expressions are exactly the same. So what this is it leads to our concept of dealing with polynomials. So that's one of our nicest forms for an expression. It's going to be your variable to a nice power, like a second power, third power, fourth power. And you can add all the terms together. So order of operations still holds in the same way. You just treat those constants attached to it and say you have 3x squared and you're adding 5 more. In total, you have 7x squared. So let's get some practice. Let's simplify each expression and remember our order of operations, the distributive property, and when you're subtracting one expression, that minus sign has to distribute out. So in this case, when we're adding these two terms, that plus sign really doesn't do anything. Everything in the second expression stays the same. So now we want to group the like pieces. We have 3x squared. We're adding 2 more of them. So in total, we have 5 x squareds. Then if we look at the next term, we've got 3x. We're subtracting 3x. Those really end up canceling. So you could write that you have 0x, but you don't need to. They just disappear. And then finally, we have plus 5, we have minus 10. So if you combine those two, you have minus 5 in total. Okay. Now for this next one, we've got that subtraction. You've got to go ahead and distribute that minus sign to every single piece. So that's minus x squared. The minus minus gives you a plus 2x and a minus 7. So before you can actually combine, this has to distribute and change every single sign. So now we go ahead and group the like pieces. I have 5x squared and I'm subtracting one of them. So in total, we have 4x squared. We have 3 x's. We're now adding 2. So we have in total 5 x's. And then we had plus 2, minus 7. So in total, that is minus 5 as our constant. Okay. So let's try this expression now. Before I can go ahead and combine these things, I've got to worry about these constants that are out front. So we need to distribute it to everything inside. So the 3 has to distribute to all 3 pieces. Likewise, the 2 has to distribute to all of the pieces. So before I combine, we've got to go through multiplication because that comes before addition. So this is 3x squared. 3 times 3x is 9x. 3 times 5 is 15. And then we distribute a positive 2 out. So we get positive 2x squared. 2 times negative 3x is negative 6x. And then 2 times negative 10 is negative 20. Now we can combine our like pieces. We've got 3x squared plus 2 more. So in total, we have 5x squared terms. And then I've got 9x. I'm getting rid of 6 of them. So in total, we have 3 x's. And then finally, if we look at our constant term, we have positive 15 minus 20. So negative 5 is our constant term. And then again, for this next one, before I can combine like things, I've got to distribute the 2 and the negative 3. So we got to be careful with that minus sign. So if you distribute the 2 out, 2 times 3x squared is 6x squared. 2 times 4x is 8x. 2 times negative 5 is negative 10. And then when you distribute the minus 3 out, negative 3 times 4x squared, negative 12x squared. Negative 3 times negative 5x is positive 15x. Negative 3 times positive 1 is negative 3. So grouping our like pieces again, start with the x squareds. I have 6 and I'm subtracting 12 of them. So we really have negative 6x squared. Then we've got 8x. we're adding 15. So in total, we have 23 x's. And then for the constants, we have minus 3, minus 10. So we have negative 13 x's. And now let's use our knowledge to go ahead and do that multiplication. Again, we can go through FOILing. So we get the first term, which is y squared, the outer, which is 7y, the inner is negative 5y, and the last, negative 5 times 7, is negative 35. So we've got two pieces that are alike. So this is y squared plus 2y minus 35. And then likewise, if we do our first term, 2x times 3x is 6x squared. The outer is negative 16x. The inner is positive 18x. And then the last, 6 times negative 8 is negative 48. We've got two like pieces, which are the x terms. So cleaning this up, we have 6x squared. That leaves us with a positive 2x and a negative 48. So now let's look at this last one. We're going to use the distributive property, and we want to see, does it match that description? So it involves multiplying every procedure in the first term by every term in the second factor. So we need to distribute this out. The first term, the 2x, only has a single thing in it, so it's coming in contact with both of the pieces in the second factor. So this is going to equal 2x times 3x, which is 6x squared. 2x times 4x is 8x. So it is the same process. Because the first factor just has a single term. So it's coming in contact with all of the other components of that second factor still. Okay. So now we'll think about trying to check our answers. So our goal was to get another expression that gives you the same output regardless of what we pick. So if two expressions that satisfy the condition, if two expressions satisfy that particular condition, what should the relationships between their graphs be? And really, if they're exactly the same, the output should be equal, so the graphs should be equal. There shouldn't be any change because it's still telling you the same information. So we went through and we multiplied this expression and found that it was equal to 6x squared plus 2x minus 48. If you go ahead and plot both of these, you're going to get exactly the same graph. So you only see one because they're just on top of each other. So yes, we are correct in that those graphs should be equal. So now let's try some multiplication. So we're going to use that process of FOILing again. So we multiply our first terms, which is y squared, multiply the outer term, which is 7 and y. The inner gives you negative 5y, and the last gives you negative 35. So the only two that can be combined are the 7y and minus 5y. So you have 2 y's and then the minus 35. For this one, when you multiply them together, the first terms give you 6x squared. The outer is minus 16x. The inner is positive 18x. And the last is negative 48. So when we group the like pieces, you have negative 16x plus 8x. That's going to be 2x minus 48. Okay. So this process is each term in the first factor will come in contact with the other terms in the second factor. So in this example, if we apply that same process with the distributive property, it's still the same thing. The first factor just has a single term. So it's still the same process. So we need to take 2x and times it by 3x plus 4. You get 6x squared plus 8x. So it's the same process because there's only one term in the first factor. Okay. All right. And so because we're simplifying these expressions and we're getting what should be exactly the same thing, regardless of the x you pick, if you plugged it into either expression, you should still have the same output. Because of that, the graph should be almost identical. So the graph just represents those input and output values. So really, the graphs should be the same. So if we look just back at this last example, we've got one expression here and another expression here. If you go ahead and plot them using a computer, here's one expression, here's the second expression. This is what the output looks like. And the reason it does is because they're overlapping. They're the same. So we can check that our answer is correct by seeing that we get the same output. Which is what we should have. So this leads into the very last thing we wanted. So this leads into the very last thing we want to do, which is going to multiply something that has 2 terms in the factor by 3 terms. And it's still the same process. This x has to come in contact with all of these, and the minus 5 has to come in contact with all of these. So we're going to first multiply x by each term of the other expression. So x times x squared plus 3x plus 4. It's going to get distributed to all of them. So this is x cubed plus 3x squared plus 4x. Now we're going to take the negative 5, which was the second term, and multiply that by each piece in the second factor. So this gets distributed to everything. So that's negative 5x squared minus 15x minus 20. So adding these two together, when you take x minus 5 and times it by x squared plus 3x plus 4, the x gets distributed to each of these. So does the minus 5. So what you end up with is x times x squared plus 3x plus 4 minus 5 times exactly this same thing. And we've done both of these. The x times the x squared plus 3x plus 4 is right up here. So that's x cubed plus 3x squared plus 4x. And then the minus 5 times that expression is right here. So that's minus 5x squared minus 15x minus 20. Grouping our like pieces, we have a 3x squared and a minus 5x. Then we have a 4x and a 15x. So I don't have any other x cubes. I have 3x squared and I'm subtracting 5. So really we have negative 2 of them. I've got 4x and I'm getting rid of 15. So we have negative 11 of them. And then the constant is by itself. So this is a process we want to keep in our mind. each term in the first factor will come in contact with each term in the second. So we're going to use this process of distribution. Instead of the 10, we're going to have the x minus 5. So this whole piece gets distributed to each component. So we'll take the x minus 5 times that first piece, the x minus 5 times the second piece. And now, to actually evaluate each of these, we'll go ahead and use the distributive property again. So the x minus 5 times the negative 0.025x plus the x minus 5 times the 22 can be evaluated just by distributing. So we'll distribute this to the x and to the negative 5. And what that gives us is negative 0.025 x times x is x squared. And then negative 5 times negative 0.025 gives you positive 1.0, gives you positive 0.125x. Now when you do the same thing and distribute the 22 to both pieces, that's going to give you positive 22x. The negative 5 times 22 is going to be negative 110. So now we only have two things that are alike, so we can go ahead and combine those. And this expression is exactly the same as negative 0.025x squared. That's going to be positive 22.125x minus 110. So this process really, if you notice, the first expressions, each piece in that factor is going to come in contact with the pieces in the other factor. So the x came in contact with both of these. The 5 also came in contact with both of these. So we can use this process to make that multiplication simpler. We also have another method that's called foiling. So I'm going to show that with this next problem. So in designing a boutique's parking lot, they have a landscaping strip on 3 sides, and an architect found that the total area could be expressed by this form, where W is the width of the paved portion they're going to have. So we want to multiply out the parentheses and simplify this expression. So I'm going to start with W plus 4 times 2W plus 8. And you're going to keep in mind that this will come in contact with both of these. Same thing, the 4 will come in contact with both of these. So the method we're going to explicitly use is called foiling. So foiling stands for you multiply the first terms. So the first term is W, the second first term is 2W. So when you multiply those, you get 2W squared. Then the O in FOIL stands for the outer. So W is the outer and 8 is on the outer side. When you multiply those together, that's 8W. I is the inner. So the 4 and 2W on the inner. So we get 8W when we multiply them. And the L in FOIL is the last. 4 is the last in this expression. 8 is the last in this expression. When you add them together, you get 32. And then these two are the ones that are alike. So the expanded expression of this is 2W squared plus 16W plus 32. Okay. So this first form is called the factor form of the expression because you have one thing times another. So these are called factors. This full expression we have is the expanded form. So both are beneficial, but they're exactly the same thing. So if you have the width of the pavement to be 10 feet, you'd plug in 10 to either expression, and you should still get the same area for that parking lot. Okay. So let's get some practice just simplifying expressions, working with what we call polynomials. So we have powers of x, but it's like a nice even power, x squared, x cubed, x to the fifth. Those are called polynomials, and you can add them together. So we can perform the same type of thing, multiplication, division, all that kind of stuff, but you have to remember your order of operations. So multiplication has to come before we do division. So if I want to go ahead and combine these two polynomials, so this first piece is a polynomial, this is a polynomial, what we need to do is first get rid of those parentheses. Now here there's nothing being multiplied on the first piece, so you just get the 3x squared plus 3x plus 5, and you're adding each of these other terms. So when we add negative 3x, it's the same thing as subtracting it. Now I'm going to combine my like pieces. So I have 3x squared plus 2x squared. In total, we have 5x squared terms. When we look at x's, we have 3 x's, but we're subtracting 3. So technically you have 0 x's, but you don't need to write that. Those really just cancel each other out. And then finally, we have this plus 5 minus 10, so that combines to minus 5. Now for this next one, before I can combine the like pieces, I've got this minus sign out front, which is like a minus 1. So it's got to distribute to everything on the inside. So the 5x squared plus 3x plus 2 stays alone. When you distribute that minus sign, it's minus x squared plus 2x minus 7. So before we can start combining, we had to distribute that out. So I have 5x squared, and now I'm subtracting 1. So in total, I have 4x squared terms. Then if we go to our x's, we have 3x plus 2x. So we have 5x. And then finally, 2 minus 7 minus 5 is our constant. Okay. So let's try some more. Again, for both of these, I've got to distribute the 3 and distribute the 2 before we can actually simplify. So if you distribute the 3 out, you get 3x squared. 3 times 3x is 9x. 3 times 5 is 15. Then distribute the 2, you get 2 times x squared. 2 times negative 3x is negative 6x. And then finally, minus 20 is the 2 times negative 10. So we combine our like pieces. We have 2x squared, 3x squared. We've got 5x squared terms. Then if we go ahead and look at the x's, we have 9. We're taking away 6. We have 3 of them. And then when we look at the constants, we've got 15 minus 20. So we really have negative 5. And then for this one, we've got to distribute this 2 out, and then we've got to distribute the negative 3. So it's going to change the sign of everything in there. So when you distribute the 2, you get 2 times 3x squared is 6x squared. 2 times 4x is 8x. 2 times negative 5 is negative 10. Now when you distribute that minus 3 times 4x squared is minus 12x squared. Minus 3 times negative 5x gives you a positive 15x. And then 1 times negative 3 is going to be negative 3. Now we can group our like pieces. We have 6x squared, but we're getting rid of 12. So now I have negative 6x squared. We've got 8x, and I'm adding 15 more. So in total, we have 23 x's. And then finally, we have negative 10 minus 3. So we have minus 13 as our constant.